So I'm going to talk a little bit about some of the nerdy stuff that we were listening to before, and I'll try to address a couple of the things that Ken was bringing up. Let me just jump right in. So over the past few years, there have been a number of developments in terms of hardware and software that are proving to be very useful for a lot of problems in economics. And in particular, how we can perform massively parallel computation. And I'm going to focus on the massively parallel type of computation that can be implemented by graphics cards. So who here has heard of graphics cards before, GPUs? So most people have, maybe for a variety of reasons. The gaming industry is largely responsible. My brother is largely responsible for the development of these devices over the 90s and the early 2000s, and I have, yeah, and I've actually never given any of my money to the industry, but I have a soon-to-be teenage son that may be taking my money and adding it to the industry, and another son following after him. But a lot of the industry is developed because of digital animation and computer games, which require heavy use of graphics and rendering pixels in parallel. And it turns out that rendering pixels, millions and millions of these things, just require simple floating point operations to be done in parallel. And that is not unlike a lot of economic or scientific problems in general. So economic problems just kind of fall into that category. So over the course of the 90s, as a lot of the animation in the gaming industry was developing, GPUs were being developed with what now we have are hundreds and even thousands of processors on them. We were talking at lunch, the latest NVIDIA GPU has like 2,500 individual cores on it. I'll tell you a little bit more about those. So originally designed for rendering pixels, somewhere around the mid-2000s, scientists realized, well, why are we not using these things that have hundreds of cores on them? They started writing in this very low-level language that allowed them to access the GPUs. And when NVIDIA caught on to that, NVIDIA is one of the major developers of graphics cards. When NVIDIA caught on to that, they decided to start developing their own software tools that would make it a lot easier for scientists like you and me to access them. Victor?
Are these single precision operations?
So they're both. And
Now they have both?
NVIDIA actually makes a line of graphics devices that are double precision. Sorry?
Now, I was telling they've always had the capacity to single or dual
Always?
Yeah,
With some weird finagling, maybe? Prior to the Fermi, they didn't. Well, there were a couple that, but not many did double precision.
It was just very slow.
So initially, they were primarily just single precision floating point. But now if you're going to be using them for gaming, you'd go for a single precision device because you can get many more single precision cores for cheaper. But NVIDIA makes a line of scientific. They actually have no hookup for graphics. You can't even use them for graphics. They're just intended for double precision scientific computing. And so I'll talk about one of those devices today. So let's see. We'll try to go quickly. So as an example, the Tesla card is one of those, the Tesla C2075. This is one that I ran the results. I'll show you an example later. The results that I'll show you, we're using this card that has 448 processors on it. Now these processors are grouped into groups of 32 cores that are called multiprocessors. And so there are 14 multiprocessors, each of which have 32 cores. And the architecture of the GPU is such that these 32 cores share a portion of the memory bank that is not shared among the others, and so on. It gets very complicated fast. I should say here, though, that so I'll give away a secret. If you're interested and you have a project already that you think you could develop for GPUs, you can actually apply to NVIDIA and NVIDIA might throw you a card or two. You just have to go and Google NVIDIA academic grant program or something like that. And last year I applied and I got 2 of these for free. They were, retail value about $2,000. And then this year I applied for 2 more and they gave me the latest and greatest, now 2,500 processor cards. So NVIDIA is actually wanting to seed the academic community with these things. So you don't have to pay. The retail value on the newest thing is $3,200 or something. So you can really save a lot of money and get started. So now, what's the difference between CPUs and GPUs? So a GPU, so most of you probably have maybe not everybody has a sense of what CPU cores are like, but GPU cores, these run at a lower clock speed relative to CPUs. So in that NVIDIA Tesla, each one of the individual 448 cores is running at 1.15 gigahertz. They dedicate far more transistors to arithmetic operations, far fewer to control flow, caching, memory operations, things like that. And they have far less memory. So you have a fixed amount of memory on a GPU. With that Tesla, you get 6 gigabytes, and you can't expand that or diminish it. It's just 6 gigabytes. Whereas with the CPU, when I built my machine last year, I just threw in 64 gigabytes, and that was expandable, right? It still is expandable.
So is this 6 gigabytes for the whole machine, or just 6 gigabytes on one multiprocessor?
For the whole GPU, for all 14 of those multiprocessors.
Oh.
Yep.
And so all of them share that same memory? Okay.
That's the global memory, and
Yeah,
some of that's subdivided into shared memory and so on.
So of that 6 gigabytes, is it all allocated to the 32 cores, each of which has 1/32 of the 6 gigabytes, or there's some portion of it that's totally global?
Yep.
All of the cores.
And I'm not exactly sure how it's portioned off. I can't remember the relative sizes, but yes, portions of it are shared just for a multiprocessor and so on.
But the 32 multiprocessors, or whatever you call them, they have their own local memory.
Yes, they do.
That is,
But that's part of the 6 gigabytes. Okay, but so where they're lacking in clock speed, clearly they're making up with sheer quantity of compute cores. So GPUs are really ideal for computational work that has what we say is a high arithmetic intensity. So lots of floating point operations relative to memory transfer and access. So for every time you're accessing memory, if you're computing a lot of floating point operations, then a GPU is likely to be very beneficial. And so the broad concept is that GPUs are very ideal for simple arithmetic instructions that are not going to require a lot of branching and memory access. Here's just a schematic diagram. If you go to the NVIDIA, if you just Google CUDA, you'll find the NVIDIA programming guide, the CUDA-C programming guide. And here's a graphic that just kind of schematically shows what these things are like. So a CPU, you might have 4 cores on your CPU. A lot of the transistors on the card are going to be dedicated towards cache, which is like quick memory control in terms of branching and so on. Whereas the GPU has many, many, many more of these algorithmic logic units that are doing the floating point operations, but far fewer transistors are dedicated towards memory and control flow. So that's where you're going to get all the arithmetic intensity because of all those green blocks. Now there's a difference between GPU memory and CPU memory, and it's very important when it comes to GPU computing. So CPU memory, I'll call it host memory. GPU memory is referred to as device memory. When you actually want to compute, when you want to perform computations on a GPU, you have to explicitly move your data or whatever it is you're operating on back and forth between the two. Well, depending on how you structure the problem, you can just initialize data objects on the GPU, but at some point, very frequently within your algorithm, you need to move things back and forth. And it's just important to be cognizant of when you're moving things back and forth because it's costly in terms of time. It's non-trivial to move things from one type of memory to the other. So where you might set up your algorithm to start computing on the CPU and then throw things out to the GPU, you have to be very cognizant of when it's requesting memory transfers. It's not a simple, you can't simply compute the time that it took to crunch numbers on the GPU. You have to take into account the time for memory transfer. So scalability is another important issue when it comes to GPU computing. So there are two notions of scalability that I should separate out. The first is scaling within the one graphics device. So within a graphics device, so Yang has his computer here. I don't know if it has an NVIDIA card. If it does, it probably has. So some of these MacBook Pros do.
Yeah, it's a hand-me-down. It didn't happen when I had it.
Okay. Okay. Well, some MacBook Pros do and some don't. If it did, it would have 32 cores in it. Now, I could sit and I could develop on his computer if it had 32 cores, write all my code, and then move it over to my machine, which has this Tesla card, and have no issues. I would not have to change a thing in my code. I can be completely unaware of the number of processors on the machine when I'm writing my code. So it's in that sense, it's very nice in that it scales within a GPU automatically. You can be agnostic of the number of processors. So the scheduler on the GPU takes care of all that transparently. And it increases the portability of the software among differing computers. So Chris, do you have a Kepler card in your machine?
Yes.
So Chris had set up a Kepler card in his machine before I got my Kepler card, and I was interested in trying it out. I just downloaded my code onto his machine directly from my Bitbucket repository and did nothing but type make run, and it just ran my code, and I saw what the new timing results were. So it's a very nice feature of GPU computing. Now, if you have multiple GPUs, then you can scale across devices by using some messaging protocol like MPI.
If I had AMD,
I'll talk about that in a couple of minutes. I'll get there in about 4 slides, AMD. So just a brief kind of segue into the next segment. So Amdahl's law, I'm not sure how many are aware of Amdahl's law, but it's important to keep in mind when you're talking about parallel computing that there is an upper bound to the amount of speed up you can get when you have multiple processors involved. So Amdahl's law basically says, let's say you have a program that you want to run. And the serial version of that program, we're going to normalize its compute time to 1. So it runs in 1 unit time. Now let's say that program, some fraction of it, p, can be parallelized, but 1 minus p of it cannot be. So what is the denominator is essentially capturing the new amount of time for the parallel implementation of that program. So 1 minus p of it, let's say 50% could be run in parallel. Then I can run the sequential version in half the time of the 1 unit, and then the remaining, if I've got 10 processors, I can take what did I decide? This is 0.5. I could take 0.5 and divide by 10. And then I'd have my new amount of time that it would run in parallel. And then I would divide 1 by that time to get how many times speed up I would get for the parallel implementation. So in the case of 2, if I had an infinite number of processors, which would be the upper bound, or I'm sorry, in the case of p being 1/2 of my program can be written in parallel. If I had an infinite number of processors, the most speed up I could get is 2 times. Now, as that fraction, of course, increases towards 1, I can get a greater and greater amount of speed up. Oh, okay. So with that in mind, the software implementation of when you want to author software for a GPU needs to keep in mind what portion of the program can be run in parallel. And so the two words that we typically use are kernels and threads. So a kernel is essentially just a function that wraps that P portion of code that you want to send off to the GPU that can be written in parallel. So the kernel is just a special function authored in, I'll talk about languages in a second, that contains the instructions that are going to be run on the multiple cores in sequence, okay? That is in parallel, but the multiple instructions within the kernel will be run in sequence on each one of the individual cores. I say the kernel only comprises a portion, and it usually is that portion or a portion of the portion that can be run in parallel. Then what happens is what you're typically doing is you have some data structure and you want to run the set of instructions in the kernel in parallel on each element of the data structure. So let's just say you have an array of 1,000 things, and you want to do a couple of operations, floating point operations on each one of those things in parallel. Then what you would do is you would pair one data element with the set of instructions, the kernel, and you would pair those with one of the compute cores, and you would call that a thread. The thread gets assigned to a compute core, okay? And it's the assignment of threads to compute cores that allow you to run everything in parallel. So the word thread is probably familiar to a lot of you if you've done any type of CPU parallelism. The idea is that you have that you're weaving, and so you have threads, and furthermore, NVIDIA refers to the groups of threads that get assigned to multiprocessors as warps, which is another term from weaving, which they claim is the first multiprocessing technology that existed, which probably is debatable. So just as CPU cores or GPU cores are grouped as multiprocessors, threads are grouped into user-defined groups called blocks. So as the user who's writing the software, you would take that array of 1,000 elements, and you might say, I'm going to block this off in groups of 100 threads. So the first 100 data elements is going to be my first block, the second 100 will be my second, and so on. And then you will assign blocks. Well, what the scheduler does transparently for you is it takes a block and it puts it on a multiprocessor, okay? One block goes to a multiprocessor, and furthermore, usually after you've blocked off your code, multiple blocks get scheduled on one multiprocessor. And then what the multiprocessor does is it breaks your block of 100 threads into warps of some 32 size, and it will move through one instruction on each element of the warp. It will go to another warp and move through the first instruction, and then go back and do the second instruction, and it just handles everything for you under the hood, and you don't have to really deal with any of that at all. It's all tuned and optimized. But so then what's going on is the way the scheduler and the cores are working, they're just kind of under the hood crunching away, kind of doing one instruction all at the same time on all of your threads. This type of architecture is known as SIMT, single instruction multiple thread. Chris?
So Eric and Matt and I are working on a problem right now using the GPU computer, and I think the problem that Matt was running into for a while until he finally figured out some command to make it fix itself was related to this, right? It wasn't finishing with something or other.
Synchronization across
Yeah.
processors.
Yeah.
So I kind of kicked out the slide that discusses branching just for time's sake. But what you really want is for these individual cores to be moving in lockstep, implementing the same instruction on each one of the data elements at exactly the same time. If the code in your kernel has a branch that says, if this happens, then do this, and it happens here and not here, then it can handle some of that, but as soon as they start to diverge too much, the whole GPU will just start to execute all of your instructions sequentially on one core, which is horribly inefficient.
That wasn't our problem, was it?
Well, the problem is if they get too out of sync and you don't synchronize them. There are ways to synchronize them at points.
Just to wait up for each other.
Exactly.
Yeah.
I don't see the value of this
it's maybe not too valuable. Maybe I should have kicked this slide out as well.
I think it's shared memory, the shared memory that is.
So in the end, if you're authoring code, if you're going to write CUDA-C code, which I'll explain to you in a second, in fact, maybe on the next slide, you have to tell it how to block off your data elements so that it knows how to pare it down for the multiprocessor. And different block sizes can be optimal for different problems, but it's kind of esoteric for the level that we're talking about today. And in fact, what I prefer to promote is a library that does all of that for you. So in the end, it's not really that necessary. So this is kind of a schematic diagram. If you were to block off your code and have multiple cores, multiple blocks will get assigned to one. Well, this core then represents a whole multiprocessor of cores. Okay, how do you really do this then? So CUDA-C, NVIDIA, as I told you on the first slide, is the leader in developing tools for GPU computing. So the best documented, let's see, I must have the upside somewhere. You know, it's the best documented, best developed. It's got the largest user community. Those are all upsides. It's essentially a wrapper language that allows you to make calls from C++ code, and I think now Fortran code, that where you can interact with the GPU. You just write your function. Essentially, for me, I write it in C++ syntax, and then I can make calls with a few wrapper functions to that function, and it knows to implement it on the GPU. The downsides, of course, are that you have to be familiar with C or C++, which a lot of economists are not. So I would love to try to convince economists that this is not very different from Matlab. It's really not. But it is a downside. The other downside is that you have to run on NVIDIA hardware. So if you're going to write CUDA-C, you can't run it on AMD hardware, which is a problem, right?
We have languages like Opencl.
Yeah. So what you have, so I should just mention the CUDA platform itself is free. It's just that the hardware, you're tied to the hardware once you've downloaded that set of tools and written in that language. Now there's Opencl. Opencl is an alternative that's very, very similar to CUDA-C. It's, I guess, open specification, and it's promoted by a consortium of software companies that call themselves the Kronos Group. Apple is one of them, and a number of others. The syntax, like I said, of Opencl is actually very, very close to CUDA-C. It has the advantage of being hardware independent, so that Opencl you can run on an AMD card. So this is, Chris and Matt have written some software that essentially interfaces Mathematica with AMD devices through Opencl. So Opencl, it can not only handle multiple GPUs that are of AMD type, but it could handle a GPU that's AMD with NVIDIA simultaneously. And it is furthermore heterogeneous in the sense that you can program, I've never done this, but you can program for GPUs and CPUs all at once. Just kind of use all the heterogeneous hardware in your computer simultaneously. The downside is I've struggled with trying to find good documentation for it and understanding how to get up and running. That is good documentation to really get your system set up with. It's been a struggle to get even just the hardware identified within the Mathematica platform. So, and it's tough to pin somebody down that really knows what's going on, because it's just kind of, it's not you know, for profit. There's nobody out there making money on it, so there's little incentive for them. So before I move on to an example, how am I doing on time? Am I 20 minutes in now? Is that okay? So there are a number of other software tools out there that are more mainstream for what economists are used to. So Matlab has a parallel computing toolbox. I've never done it, but it may. So the Matlab parallel computing toolbox is basic, as I understand it, just a bunch of canned functions that will speed some things, like say matrix inversion. It will just kind of do it for you. But if you need to write an algorithm in a more specialized fashion, you'd still want to write some CUDA-C kernel and pair it with Matlab. I think that's possible. I've never done it though. Mathematica has CUDA link, which Chris and Matt have been working on. An Opencl link, and this does allow you to write author a kernel and link it into Mathematica. I intend to, at some point, I'm learning Python, and I intend to learn PyCUDA because I hear that's one of the great advantages of Python, other than being open source, is it interfaces really well with C, and I believe with CUDA as well. And then there are a bunch of other third-party software vendors out there that have libraries of, matrix libraries and all sorts of things to accelerate your code. One that I really like is down at the bottom. It's Thrust. Thrust is the one that I mentioned that it's a template library that I use in my C++ code that eliminates a lot of the kind of nitty-gritty coding details that you would otherwise have to write. And it handles all that blocking for me. It's highly tuned, and I found it to be much faster even than my own CUDA-C code. So I'm going to show you Thrust results at the end of this example that I'm going to show you now. So the example, so I guess I should pause and say, are there any questions before I move on to a quick example and show how I've applied this?
The bottom two options, these are to use graphic processors, or these are just general purpose libraries?
These here?
Yeah.
So Thrust has a backend, I'll talk about it, for OpenMP. So it's not just graphics. I don't know about VNSCL. I think this is just for graphics devices, and I believe this, I'm not sure about, I know these are for GPUs. I'm not entirely sure if they make use of other resources. Other questions? I guess it might be a good moment to touch on what Ken was badgering Michael about earlier with the, so Ken was talking, so the value function problem, I was actually really happy to see that Michael had used the graphics card to solve that problem, because it's a problem that is very well solved by a graphics device. I wrote a paper with Jesus Fernandez Villaverde and Juan Rubio and Ron Gallant a few years ago that it looked at a dynamic programming problem and showed how much of a speed up you could get. But as I've been working on a lot of this information is actually, I should put a disclaimer out there. Well, not a disclaimer, but just for your information. A lot of this information is encapsulated in a forthcoming chapter in the Handbook of Computational Economics, which I'll put on my website today. Yeah, that is, so what I was going to say is as I was working on that chapter, I had to mollify some of my results with GPU computing, because we had some referees that were they were computer scientists that were hounding me on a lot of the details in terms of multi-core CPU computing. And rightfully so, it turns out that the results, if you're really fair about comparing a full GPU with a full CPU, all the cores on a CPU, if you're fair about the cost comparison of buying a multi-core CPU versus a GPU, and if you're fair about how you tune the code for that CPU, then the results become a lot softer in terms of where before I was getting 200 to 500 times speed up for my value function ituration, now I was looking at more like a 5 to 10 times speed up. And when you accounted for dollar cost, then it was becoming more of a wash.
$0 in your case.
So I've got an infinite amount of dollar speed up, right? So as academics, we have the pleasure of having an infinitely productive device on our hands. But I guess that's a caveat to say that some problems are better suited than others. But the other part of that is that the only way I got the really fast CPU speedups for that value function problem was after I had coded everything using the thrust library, and I used the thrust library to implement, I used the thrust backend for OpenMP on my CPU, my multi-core CPU. This was what tuned it to be so fast on my CPU. So it turns out thrust, and the beauty of thrust is I took the exact same code and just flipped a switch in my makefile, and I said, compile for OpenMP instead of CUDA, and it ran it on all 4 of my CPU cores instead of all 448 of my GPU cores. That's all I did, and I could compare the two. And then I could get a dollar cost comparison as well. So, but I never would have gotten there if I hadn't used thrust, which is an incredible library of functions. It's a matrix library, essentially. Okay, so, but let me talk about another problem that I've worked on that really still has a huge benefit even once you take into account all of these things. So this is a paper I was working on last year and a half or so. I'm not going to talk about the economics about it, except to say that it's a model that looks at heterogeneous beliefs and how it affects asset volatility and trading volume simultaneously. Okay, so I just take a standard kind of Lucas economy. What you saw with Carl's paper earlier is very similar to the setup here. So it's a very similar type of Lucas tree economy where I endow agents with heterogeneous beliefs about how that tree is going to drop fruit every period. So they have heterogeneous beliefs about the aggregate endowment. Okay, and it's the economic purpose of the paper is to discuss how asset exchange occurs and volatility occurs for those assets. But what I'm going to talk about is the computational details. So let's just say we have some number of periods. I write it here infinitely just in the general specification. I'm going to compute a finite version of this. And we have some set of states every period, and which we denote S sub t. So you can think of a high and a low state. So S sub t is either an H or an L. And then S super t is going to keep the whole history of states logged. The history of states is important for this problem because of the heterogeneous beliefs. We can furthermore say there are I types of agent or I agent types. Okay. There's a whole continuum of population, but we segment them into types of agents. And the population proportion then I will denote by mu. I leave it here as if it's potentially state dependent, so the proportions could be changing through time. In practice, the results I'm going to show you just fix the population proportions for each agent type at various values. So there's a single consumption good. It's dropping fruit. There's an endowment. There's a single tree dropping the consumption. The endowment is that each type receives fruit in its relative proportion of the population. I use a constant relative risk aversion utility function here, so it has the standard Inada condition properties. Now, the aggregate state then is going to follow this is an S-state Markov process, which is evolving as you would see with these conditional probabilities. The heterogeneous beliefs then enter here, where there's a true process that governs the movement of the aggregate states. Agents then don't know what that true process is, and they will have differing beliefs on how the state evolves. So this is essentially the maximization problem. This is a very easy maximization problem to set up. You can find it in Lundquist and Sargent. Now, what's important, though, is that in this problem, I'm keeping track of these probabilities. And these probabilities are extremely important when I look at first-order conditions. So we set up the problem. I'm looking at it in terms of, at the moment, in terms of state contingent consumption. These are complete markets, so I'm allowing them to purchase the consumption asset at each possible state. If I draw it out, I could say, essentially, if we just have a high and a low state, then you know, we just have branches that keep going and growing exponentially like this, right? So what's going on then is the agents want to maximize their lifetime utility subject to their lifetime budget constraint here. And we get first order, or okay, I define the competitive equilibrium just so that I get the aggregate resource constraint defined. But the first order conditions for the agents are very easy. We get the standard Euler equation. And I'm doing this state by state, so there's no expectation here, but I do have the probabilities. And then I take the ratio of Euler equations. I choose agent 1 as the reference agent, and I put his Euler equation in the denominator so that I have my intertemporal condition here, which is one Euler equation above the other. Now I can solve this in terms, what I do is I solve this for this consumption variable at S super T for some agent I in terms of everything else, okay? Given that I've got some nice utility function, I can do that. I can put everything on one side, invert the utility function, and that's what I have here. So now what do I have? I've got the consumption for agent I at some state, pick a state, defined as this function of a bunch of kind of economic primitives, consumption for all the agents or the agents at the 0 state, and the consumption for the reference agent at that same state that you're trying to solve for. Plug this into the resource constraint, which holds an equilibrium, and what you get is you now have one variable, which is the reference agent's consumption at S super T, as an implicit function of consumption at time 0. So given that you know consumption at time 0, you can solve this function implicitly for that right there, okay? It's important that I'm keeping track of this ratio of probabilities. This is very important for the model and for the results, the economic results. To solve it, though, what I need to do is I need to solve that problem right there for every one of the nodes in the state tree. Okay? Maybe I've got the picture here next. So at every node here, I'm solving this one equation, a single equation with a single unknown, conditional on some consumptions that I start with at the root. Now, if I knew those, then I could solve it in one shot and be done. I could solve as many periods forward as I need to. Given that I don't know the consumption initially, what I do is I take a guess, I solve forward, I check for consistency of my solution using the budget constraints of the agents, and if they're off, I modify my guess at the root and I iterate. So I have an outer iteration loop that's solving a bunch of single nonlinear equations with single unknowns at each node. But the beauty of the problem here, the way it's structured, is there's no dependency among the nodes. This guy's consumption here only depends on consumption at the root of the tree and nowhere else. So I have a perfect setup for parallelism here, where I could have, if I solve this, essentially what I do in the paper is I calibrate a quarterly version of the model that's tied essentially to business cycle consumption dynamics, and I can solve it up to 30 periods forward, which has 2 billion nodes in that tree. If I were to solve that on my CPU using all 4 cores and all the optimizations I was talking about using thrust, that's going to take me some 7,000 seconds, which is, how long is that? A couple hours? I mean, half a day or something? Is that right?
2 hours. 3,600 seconds.
There we go, a couple hours. Whereas I can do it in a minute on my GPU, because my GPU is going to go and crunch away at each iteration. It's just, I can take all of these billions of nodes, I can block them off, or thrust blocks them off for me and just throws them out to the GPU processors. And it's an easy problem to solve. It's a single equation with a single unknown. It takes a few Newton steps, right? And it can solve that, or maybe even analytical steps, and then report back. And I can check the consistency conditions back on the CPU and then iterate again if I need to till convergence. So that's that's essentially a brief example, but that's not the only example. Like I say, value function iteration is another good example that can exploit this. In fact, GSSA is an example that I've coded. Yan Yang is working on another parallel implementation of GSSA. There are all sorts of problems, and I should just conclude by saying that clearly not all problems in economics. This is no panacea. Not all problems are appropriate for this type of parallel computing paradigm. But what I find more often than not when I'm talking with people, what you think of, if you start thinking the right way, you'll find ways to parallelize and actually get quite a bit of speed up that you never would have thought of. It's just not really there initially. You have to kind of dig deep and be creative and think hard about it. So we're talking about solving these micro DSOPs, whatever we call them. But a lot of econometricians have taken to GPU computing using those that are interested in estimation using particle filtering. It's another good application. So there are there's a lot of potential for a wide variety of economic problems. So we might be out of time now, are we? Okay.
I need to
Oh, yeah.